All right, let's just continue. And we have done inverter, NAND, and an OR. And analyze them, show the expressions, show the very long description for them, and everything else. Okay. See what we have done so far. The NAND gate, we have several transistors in the pull down structure, several transistors in the pull up structure. They are either in the pull up, they are parallel, in the pull down, they are in series, or the other way around. Okay. And but then why not have a combination of them, meaning that we have two transistors maybe in series and then in parallel with the third one. What happens then, still trying to keep the complementary nature of this structure, what happens then, we get a more complex logic structure. And by the way, these are referred to as complex gates. Okay, so anything beyond a NAND and a NOR is called a complex gate. And something I really want to mention, which is quite important here, is that see, when you let me go back to the previous one. When you do the NAND, when you analyze it this way. You say, here I have this transistor A, this transistor B, and when you are trying to write the functionality of it, you just look at this. Just look at this. You say, well, I'm going to send a zero. Therefore, the W is, since you say I'm going to push a zero, therefore, the W is the complement of, okay, let's continue. I'm going to send a zero when A and B are 1. A and B are 1. So when you say I'm going to send a zero, you just put a bar. When you see when you see transistors in series, you AND them together. Okay, let me read this same exact structure in a different way. Okay, B. And this is your output W. Let's read it in a different way. I'm going to send a 1 through. I'm going to send a 1 through. That was sending a 0. Now I'm sending a 1 through, and therefore I don't put the bar. Okay, I don't put the complement. And then you say, well, I'm going to send a 1 through if A is 0. Okay, if A is 0 because of that bubble on the A input. Now, since they are in parallel, then you say or B is 0. Okay. Now, if I want to show the logic for the right-hand side, I say, well, the logic for the right-hand side is this A, B, bubble, bubble. The logic for the left-hand side is A, B, and then a bubble, which is the result of that bar on the output. Okay, so these two things are exactly the same. Now, then you say, well, only the pull-up can give you the logic function, or only the pull-down can give you the logic function. And therefore, the correct pull-up for the left-hand side is just the complement of the pull-down. So let's, without looking at the right-hand side, let's do the complement of the pull down. The complement meaning that if A is 1, then A is going to be 0. Okay, that means the complement of it. If B is 1 down there, B must be 0 here. That means the complement of it, and therefore there is that bubble. If these two transistors below are in series, the corresponding transistors up there have to be in parallel. And therefore, this is how you come up from the, you extract the pull up from the pull down. Let's do, again, without looking at the left-hand side, let's look at the right-hand side and then come up with the complementary structure down below. I say, well, I have two transistors up there that are in parallel, but then they have to be in series here. The two transistors in parallel up there are taking or are complementing, and therefore they have to be non-complementing down here, and therefore you extract this from the pull down. Same thing with the NOR gate, and then again, there are two ways you can read the NOR gate as well. The reason I said this is because this is a NAND, this is the simplest structure, and now we are going into a more complex structure. Okay, notice again, if you want, don't look at the top and only look at the bottom. Okay, and let's extract the equation for it. Okay, this is my W output. This is my W output. And down below, I have two transistors in series, one transistor in parallel. Okay, let's read this. I'm saying, notice I'm pushing a 0. See, I'm pushing a 0 either through this path or through this path. But see, I'm pushing a 0 anyway. And therefore I say my W is, I am pushing a 0 either through the left-hand side path, which is A, or through the right-hand side path. The right-hand side path is ANDing of B and C, and therefore this becomes A or B and C. Okay, you want to put parentheses to make sure that the precedence is followed, but then ANDing has higher precedence than ORing, and therefore you don't really need the transistors. Let me do the exact same thing, this time coming from the top. Okay, this time coming from the top. Coming from the top is, okay, I send the 1 through to the output through the left path, or I send the 1 to the output through the right path. And therefore my W is, okay, my W is, let's look at the left path. The left path takes C, okay, perhaps I want to do it this way. It's easier. I'm going to do this in series with this. Okay. So the top part of the top, it says I have to, I will get a 1 on the output if C is 0. Okay. Now, since it is in parallel, it means that they are being ORed together. C is 0, and then B is 0. Okay, but then that's not enough, because I also have to have, if I want a complete path, I have to have this transistor also conduct, and therefore this has to be ANDed with A. complement. Complement because the bubble. Okay. The two equations I show for W are exactly the same. When we go to Boolean algebra, we will prove that these are the same. But then I didn't do any Boolean algebra. I read the logic. I read the circuit logically. Okay. Read the circuit logic is saying the 0 pushes through, therefore you put a bar on the top, you push through a 1, therefore you don't put a bar. But then because the bubbles, you have the A's and B's and C's are barred or bubbled. Anyway, what I refer to this is AOI. Look at the function to see what it's doing. Look at the lower function, this one over here. It says W is B and C ANDed together, ORed with A. So it's AND, this is AND, this is OR, and then you're putting an invert, and therefore this is called AOI, AND OR invert structure. These are complex gates, and then there is no limit as to how complex the complex gate gets. And you can replace several layers of ANDs and ORs with one of these complex gates, but then there is a limit, and that is you cannot put too many transistors in series, or you cannot put too many transistors in this structure because of the timing and all that. Remember when we talked about the delays, we said, well, series transistors add delays, meaning that if you want to push a 1 through, all the series transistors have to conduct before you can send a 1 to the output. And therefore, if you have 10 series transistors, that's going to be a lot of delay there. Nevertheless, what I have here is AND OR invert, which is the this one. Okay. Or look at the blue representation. The blue representation is this, which is B bar, C bar, or together, and the A bar ANDed with it. Okay, so these are the structures that we represent this transistor structure. You can call, you can use either one of them. All right. Or you can put two paths down here. See, you can do A, B, C, D, A, B, C, D. Okay, and then this is the you can and then here W is you push a 0 through if A and B or C and D. This is also AOI, but this is the 4-input AOI. A multiplexer is also an AOI. Okay, a multiplexer works like this. If select is 0, you push, let's see, if select is 0, A goes through. That's why the 0 is right next to A. And if your select is 1, then the lower input, that means B goes through. So you are selecting either A or B. This is called a multiplexer. That means you multiplex A or B on the output Y. This is a 2-to-1 multiplexer. You can have 4-to-1 multiplexer, meaning that you select either A, B, C, or D. You can put these multiplexers together to make them larger multiplexers. This is a gate level structure for the multiplexer. Notice that again, if S or select is 0, the upper path becomes active, and therefore you push. Let me do S is 1 first. Therefore, you push B through, okay, because of this lower path. And then if S is 0, then this becomes active, and therefore A passes through. You can build this structure using complex gates, okay, and that's not going to be difficult because you have and ORing here, and I just showed you and ORing. It has an invert, and then you can put another inverter to remove the inverter or whatever. Something I had to mention over here. Notice that this is a complex gate, and when you have a complex gate, in order to show that this whole thing has one pull-up structure, one pull-down structure, then you don't put a line between the two gates. Okay, you just attach the gates together to symbolize the fact that you have a pull up and you have a pull down. And this was the multiplexer. Here I'm probably implying that I have a separate AND gate, I have a separate OR gate for building this structure. And the expression for this is y equal s bar a or sb. These are Boolean expressions. We are casually using them now until we get into Boolean algebra, that we will be showing the manipulation of these expressions and so on. Okay, this is the Verilog representation of it. Look, I can do a million different things. I can take this structure, form a complex gate structure of it using transistors, something similar to this. Okay, and then write the transistor structure for it, which will be, let me just and or 1 2 3 4 4 5 6. There will be 12 transistors altogether if I were to build this using here. Okay, this is A, this is B, this is S, this is S bar, okay, this is the lower part. But then what this is going to give me is the complement of the multiplexer. So what I'm going to do is I'm going to put an inverter in front of it. And therefore, this is the max output, or the Y output as we are calling it over here. What I have to do now is do the pull-up structure. For the pull-up, whatever is in series below will become in parallel up there. So let's do this, this, this. And whatever is in parallel, that means the right-hand side, the equivalent of it has to be in series with what I have there, which means this. And then I'm going to show you the lines using different colors so they don't cross. So this is what goes to this and what goes to this. The right hand side, this goes to this. Maybe this goes to this, and then this goes to this. Okay, so that's the transistor structure for the multiplexer. And I have 8 transistors in the middle, and then 12 transistors all together. I can describe this using 12 transistors, and that will give me very, very precise timing. Well, very, very precise timing as far as Verilog can give me. But then maybe I don't want to go through this simulation, so I can do it using AND gates and OR gates, just like this one. Use primitives, ANDs, and ORs in Verilog. Okay, that would be a better timing, but then I'm not doing this. I'm going one step further into abstraction, and instead of everything that I said, what I'm going to do now is write assign, okay, because for such a complex gate, there is no primitive, there is no AND, there is no OR, there is no NAND. Remember, we use the NAND primitive for the NAND gate. But then for this, because I'm just making it up, or for this, because I'm just making it up, there is no primitive, and therefore, if I want to write this, I have to write it using my own expression. Okay? My own expression, and therefore this is how I'm doing it. I just say assign and give it some time. Where do I get this time from? Well, supposedly I go into the transistor circuit, simulate it, analyze it, and then come up with this 40 nanosecond delay. And then I say, let's read this. Y is, if S is 0, this is tilde S, that means if S is 0, then A, otherwise B. Okay, if S is 0, A, otherwise B. And so this is a multiplexer, a complex gate structure, and now I am showing you one level of abstraction, one more level of abstraction. Now that we are at this, if I were to do this, using assign, I would do exactly this. Assign. Okay. Let's say some delay. 36, just made up something. Assign W equal tilde A, and it with B or C. This is then a sign expression for representing this complex gate structure. XOR is another complex gate, but then Verilog also has a primitive for it. So you can just say XOR and give it some delay, let's say 8 nanoseconds, and then say G1, that means this is gate number 1, and then you say WAB. This is a primitive for it. You can do this, or you can write an assign if you want. If you write an assign, you write something like assign W is as simple as this. Okay, and then again you have the option of putting some delay here. XOR means this. If A is 0, B is 1, the output is 1. If A is 1, B is 0, the output is 1. It's like OR, except that is XOR, meaning that both of them cannot be 1 for the output to become a 1. And the expression is this, and this is the gate structure according to this. Again, I could build a complex gate structure with this. Here I'm saying, let's say I have an AND with inverted inputs, and then an OR. I can build it this way, or I can build a complex gate. Okay. In any case, this does an XORing.